As we stretch further from Earth, our biggest enemy becomes not the cold or the void, but inertia. With chemical rockets, we can escape Earth's gravity. With fusion drives or antimatter, we dream of achieving relativistic speeds. But there's another method, quieter, sleeker, and already tested in the cosmos: solar sails. Imagine a spacecraft not propelled by fuel, but by light itself. Solar sails work on a surprisingly simple principle. Photons, though massless, carry momentum. When they bounce off a reflective surface, like a vast sail, they impart a tiny push. Over time, these pushes build up. No engines, no fuel tanks, just momentum, patience, and physics. But the simplicity ends there. To make a solar sail practical for interstellar travel, the sail must be enormous, spanning kilometers in size, thinner than a human hair, and perfectly reflective. It must maintain its shape across decades of flight, survive micro-impacts from space dust, and resist warping from solar radiation. We're talking about building a city-sized sheet of material, deploying it in zero gravity, and navigating it through space like a cosmic galleon. Even more challenging, solar sails rely on sunlight, which diminishes with distance. The gentle push that works near Earth becomes negligible beyond the orbit of Mars. That means solar sails are ideal for acceleration only in the inner solar system. After that, their usefulness fades. So how do we keep pushing? Enter the next evolution: laser sails. Instead of relying on the sun, we fire high-powered lasers from Earth, or from orbital platforms, directly at the sail. These concentrated beams can push the spacecraft long after it leaves the solar system, theoretically up to 20% the speed of light. At those speeds, a spacecraft could reach Proxima Centauri in just over 20 years. It's not just theory. Projects like Breakthrough Starshot are already working on this idea, aiming to send gram-scale probes to Alpha Centauri using lasers and sails. These probes would be small, like microchips, but fast, very fast. Scaling this up to a human mission, however, is another story. To keep a laser focused on a sail that's tens of billions of kilometers away, we need unbelievable precision. Pointing accuracy measured in fractions of an arcsecond. The laser infrastructure on Earth would need to be massive, consuming gigawatts of power and synchronized with extreme accuracy. There's also the risk of deviation. Even a slight change in sail angle could cause the beam to miss, leaving the ship adrift in darkness. And what happens when the laser turns off? The ship coasts. It can't decelerate unless a similar laser array exists on the destination side, a current impossibility. Still, the advantages are stunning. No onboard fuel, no heavy engines, just payload and sail. Maintenance is minimal, acceleration is smooth, and speeds are unmatched. One radical design proposes swarm-based sails, fleets of tiny probes traveling together, communicating via laser bursts, and sharing sensor data. If even a fraction of them arrive, the mission is a success. Another concept uses plasma sails, interacting with the solar wind instead of photons. They behave like solar sails but respond to charged particles, offering different control mechanisms and possibly working farther from the sun. But perhaps the biggest shift is philosophical. Solar sails represent a paradigm change. We're no longer blasting our way through space. We're catching the wind of the cosmos. It's elegant, efficient, and strangely poetic, traveling not with fire, but with light. It connects us back to ancient explorers who once crossed oceans under billowing sails. Now we raise our masts to the stars. At infinity beyond, we believe the future of propulsion might look more like origami than engines, and that light could be our ladder to the stars.